Alright, welcome back to Earth and Space Science. This is Mrs. O'Neill again, here to just talk to you about our next day of notes, which are going to be about pressure and weather. Yesterday we sort of introduced the topic of weather and we talked about some of the major contributing factors, things like wind, dew point, humidity levels, stuff like that. And all of that really comes back to the air around us. And the governing factors for air are temperature and pressure. We already talked quite a bit about temperature, so today we're going to focus on the pressure component. So, atmospheric pressure is the pressure of the air around us. As we're sitting here, we're literally under pressure because there's air all the way around us, similar to the way that a deep ocean fish is under pressure just by living at the bottom of the ocean. We're living at the bottom of the ocean of air. We call the pressure of this air, the inwards force pressing around us, barometric pressure. There's a similar but slightly different type that has to do with the column of air above our heads, because remember, our atmosphere is deep. It goes up hundreds of kilometers, and all of that is pushing downwards because of gravity. That's the hydrostatic pressure, the downwards pressure, just from the column of air directly above us. Every square centimeter of that column of air has a mass of 1.03 kilograms, or 2.3 pounds. A square centimeter is very small. Centimeters are about half an inch. And so this is about a quarter of an inch. And so if you think about it, we're under hundreds of pounds of pressure every moment of our lives. We're just not usually aware of it. Just the way that deep sea fishes aren't aware of the water pressure until they're taken out of it. Now, deep sea water fish, if you pull it up to the surface, it's not going to be pretty. Their bodies can't really cope with that pressure change very well. Same thing with humans. If you put us in a vacuum, we can kind of get kind of icky, but we don't like pop like or anything. It's not, the pressure change isn't enough to rupture our skin. Just lack of air to breathe and temperature changes are actually more dangerous. Okay, so how do we measure pressure? There's a couple of different units. The most obvious one is atmospheres, where we compare it to the Earth's atmosphere. Or if we want to measure it in a little bit more detail, we can have pascals, or more often kilopascals, or the standard or the old-fashioned way was with millimeters or inches of mercury, which you see as mmHg or INHg. Hg is the elemental symbol for mercury. This is because our old barometers, the tools that we used to use to measure pressure, were literally a pool of mercury sitting in sort of like a U-shape opening. So it'd have like an open pool, and then the air pressure would push it down and up into a tube on this side, a long, tall, straight tube. And we would literally measure how many inches up the tube the mercury went. Kind of weird, but it works, because that would change based on our daily pressures. Oh, and there's our noon alarm. But, okay. So, conversion factors, we're not going to do any math with this, but just so you know, one atmosphere, which is the Earth's atmosphere at sea level, is about 101,000 pascals, or 101.3 kilopascals, because a kilopascal is 1,000 pascals. That's 760 millimeters of mercury, or 29.92 inches. Can you imagine that? A column of mercury almost 3 feet tall, being raised up just by the power of our atmosphere, the pressure of our atmosphere. Okay, so what factors determine pressure? Well, altitude is the most obvious one. As you move higher up in elevation, because you're climbing a mountain or driving to Colorado or whatever reason, it decreases by 1.2 kilopascals per kilometer that you move upwards. This is actually how we measure height. With like an airplane flying through the air, we're not going to try and use radar or something to ping off the ground below us. There's an atmospheric pressure sensor built into the airplane that measures the air pressure around the airplane and calculates how high up they are. There are also pressure cycles. The atmosphere is very fluid. It can move and flow around, and it's under gravitational effects the same way that the water in our oceans is. The moon's gravity tugs on it, so does the sun's gravity, and so we end up with atmospheric tides the same way that the moon's gravity causes water tides. And so there's thick and thin spots once or twice a day as the Earth is rotating and the moon is turning around us. Under a high tide, there'd be a thicker atmosphere and higher pressure. Under a low tide, there'd be a thinner atmosphere and lower pressure. This isn't the one we're most used to, though. The pressure cycles are not something that we think about too much, but they do cause pressure systems. You've seen these on weather maps, where it says high and low pressure. Mostly these are caused by temperature differences. Where it's warmer, the pressure will be lower because the gas is expanding. Heat causes thermal expansion, and that decreases its density and results in lower pressure. Where it's cooler, it's higher pressure because as it cools off, it gets denser. And so the temperature difference between the air and the water and solar heating, all of these things can cause temperature differentials, which lead to different pressure systems. A low pressure system occurs, remember where it's warmer. The air near the surface is trying to rise upwards. This can create clouds and precipitation because as it moves upwards, it hits colder temperatures and the water starts to condense outwards. Really strong low pressure systems are associated with some of the strongest storms on Earth. The eye of a hurricane is an extremely low pressure zone right there in its eye, and it creates this sort of circulating vortex. Even tornadoes, even though they're so much smaller, have an eye. There's a localized low pressure area that can help contribute to those swirling winds. Then on the other hand, you can have a high pressure system. The air is really dense and thick. It's not floating upwards, so it's staying close to the ground, and dry air from the upper atmosphere can come further down. It creates sunny, clear skies, usually light winds. High pressure systems can be dangerous because they can sort of act like a lid or a cap over a valley and end up trapping air pollution. And so in places where that's an issue, like some of the major cities like San Francisco or LA, just something to keep an eye out. If it's a bright, sunny, clear day, it does not mean the air quality is necessarily good. Rainy, cloudy days actually tend to have better air quality because the water is literally cleaning it out. Okay, so we make maps based on these pressures to sort of predict where things are going. They're called isobaric maps. The baric here is similar to the bar and barometer. It means pressure, basically. So iso is a prefix that means equal. So these are equal pressure maps. Basically, they put a bunch of numbers on the map, and then they draw lines that connect all the ones that have the same numbers. So the lines sort of meander through areas that are at the same pressure, and they'll circle around high and low pressure zones. And you just need to track which way the numbers are going to see if it's going towards a high or towards a low. So here, we have one that's 1016, this one's 1020, this one's 1024. They're all circling around this high pressure zone. And then coming down, there's a 1012, 1008, 1004, and that's circling around that low pressure zone. We can use this to predict which way the wind's going to blow, because the wind will blow from the high towards the low. And so in this case, in this map, we would end up with a southeastern wind blowing from here in the Dakotas or Wyoming, or I'm not good at geography at these. I know we're here, but that's about it. Okay, so we're blowing from the high to the low, and then the stronger the jump, the faster the winds will be. So the closer these lines are together, the higher the wind speeds are. These ones are pretty well distributed. They're not particularly fast winds. Oh, I do want to show you something. I'm going to pause this for 1 second. Okay, this is what I want to show you. This is an online wind map. It's showing real-life wind speeds across the entire United States. And what we're looking for are places where they're circling, like right here. See how there's kind of an eye going on right here? And how everything's moving away from that eye? This would be a high pressure zone. It's moving things away. And then if it's got a spot where it's circling in, pulling the wind in, these would be a low pressure zone. Probably somewhere up here there's a low pressure zone. And you can see here it tells you what the colors mean. The brighter the white, the faster the winds are going. So up here we have some pretty fast southerly winds blowing. And then, we have some milder, those are northerly. No, they're from the south. They're southerly winds. Down here we have some milder northerly winds that are coming from the north. We're pretty close to this high pressure zone. I mean, there's Denver, so we'd be like right about here. If you look outside, maybe this kind of matches what you see. Or maybe not, because I took this recording on Tuesday and now you guys are watching it Thursday, so I guess not. But anyway, so I wanted to share that with you. So, please use these notes to finish the worksheet, and I will talk to you guys again later. Thanks for your time. Bye.